Hello there, mathematicians. Welcome to episode 11 of Math 141 Recitation, Summer 2020. Today, they see me rollin', they rating. I hope that reference isn't too old for some of you. Now that I think about it, that song, I think it's just called Rollin', if I'm not mistaken, by Chameleonaire. It was popular whenever I was a kid, so I hope it's not too old for you guys. In any case, today we have 3 sections, so big day on tap for today. We have 3.10, which looks at related rate problems. These are great. They're very applied problems where we're applying calculus to real-world situations. And we get to draw lots of cute little pictures. So I love these. I'm excited to do a couple of them with you. Then section 4.1 looks at extreme values of functions. So we look at how we can use the derivative to help us find where a function is at its biggest, at its smallest, both over its entire domain and over smaller intervals. And finally, section 4.2 introduces us to the mean value theorem, which is arguably one of the most important theorems in calculus. We also look at a special case of the mean value theorem called Rolle's theorem, which is actually proved in the book before the mean value theorem, but again, really is just a special application of the mean value theorem. So lots in store for today. Should be an exciting episode, but they all are, I know. They are all just so wonderful. Today, I'm going to get started right at the beginning. This problem, I don't think will be terribly difficult, but I think that the ideas which we use will help set up our related rate problems, which we'll spend quite a few minutes on. So let's go ahead and do this one. So here we are told to assume that x equals x of t, and y equals y of t. Okay, so x and y are both functions of t. Let me write this on a new line. Let's not do that. Let's do this. Let y equal x squared plus 3. And dx dt. I'm so used to saying dy dx, but here it's dx dt equal 5 when x equals 1. Okay, so this is the information which we are given. Our instructions then tell us to find dy dt when x equals 1. Okay, so we are looking for the derivative of y with respect to t. So here, we do have something. So at the end of last time, we talked about implicit differentiation. We introduced that new technique of taking derivatives. And remember, we said, so implicit differentiation is usually used, it's usually used whenever we can't write something like y equals some function of x. Usually used when we can't write y equals some function of x. However, in this case, that's actually going to be what we want to do. Because, however, even though we have y equals a function of x here, since we want the derivative of y with respect to t, that's the key, we don't want dy dx, we want dy dt. Dt is the kicker here, not dy dx. We still want to use implicit differentiation here, because that will help us get this derivative in terms of t. We could very well just take this derivative like normal and get our derivative in terms of x, but that wouldn't give us our derivative in terms of t. Implicit differentiation. Okay, so here's how I look at this problem and how I think about it. So what I'm going to do is I'm going to take this function y equals x squared plus 3, and I'm going to differentiate both sides with respect to t. So let's write it. So we have y equals x squared plus 3. I'm going to differentiate both sides with respect to t. Part of the advantage of doing this, or part of why we might be interested in doing this, is that if this was a real-world problem, in fact, as we'll see in a few minutes with related rates, we might want to know how y, for example, if t is time, it's probably going to be more helpful for us to know how y changes with respect to time than, I don't know what x is. Maybe x is some other quantity. Usually time is a pretty good thing that we want to know the rate of change with respect to. So let's go ahead and differentiate. When I take the derivative of the left-hand side, well, I just get dy dt. Okay, so that's how, remember, we're treating this basically like implicit differentiation. So I'm getting dy dt on the left. Now on the right, and the reason this is just dy dt is because whenever I take the derivative of y, I get 1. Now on the right-hand side, when I take the derivative of x squared rather, I get 2x. And I'm going to multiply that by dx dt. Remember, whenever we did implicit differentiation, every time that we took the derivative of y, we wrote a dy dx. Here, since both x and y are kind of, they're not the variable that we're interested in. The variable that we're really interested in is t. That's why we still that's why you put a dx dt with the dx. And whenever I take the derivative of 3, that's just 0. So now I have dy dt equals 2x times dx dt. So this gives me a formula. However, what we want is we want to find dy dt when x equals 1. Well, I noticed that when x equals 1, we are told that dx dt is 5. So we're going to use these two pieces of information now. And we go down here. Well, that means that dy dt, so we're going to plug in our stuff, plug in the given values. And this will give me dy dt equals 2 times, well, we wanted x equals 1. Let me copy down our values here. X equals 1, dx dt equals 5. Okay, so 2 times, well, x is just 1. And dx dt is just 5. And so this is just 10. And indeed, that is the correct answer. Again, this problem itself isn't terribly difficult. Once the setup is the tricky part, right? The setup is certainly tricky. I'm not saying that part is not challenging. But once we understand the setup, from there, the derivatives we're taking are really not so bad, and we're just plugging some values in. So let's review real quick what the big picture idea was. We wanted to find the derivative of y with respect to t. Right? We wanted this dy dt, but we were given our function y as a function of x. So we used the same ideas as implicit differentiation, and we took the derivative of both sides with respect to t. So whenever we do that, every variable besides a t, which in this case we didn't have any t's, whenever I take the derivative of y, I stick a dy dt there. And whenever I take the derivative of something with an x, I stick a dx dt there. And then we were given specific values that we could plug in. That final part, what you're going to do from there will depend upon the problem, but in this case, it was as straightforward as just plug in a couple of nice values. But sometimes things are a bit trickier, which we will probably see later on. The next problem, which I would like to do, is problem 3. This one has 2 parts, and I think I'm just going to do the first part and leave the second to you. They're quite similar. So the original 24-meter edge, length x of a cube, 24-meter edge length x of a cube, decreases at the rate, decreases at the rate of 2 meters per minute. So 2 meters per minute. So then there are two parts of this problem. Again, we're just going to do the first part, and part A asks, when x equals 2 meters, at what rate does the cube's surface area change? Okay, when x equals 2 meters, at what rate does the cube's surface area change? Well, the first piece of information we're going to want is we're going to want a formula for the cube's surface area. That seems, I think if we don't have that, we're going to be in trouble for the rest of the way. So let's go ahead and figure that out. I'll admit I don't have this one memorized, but that's because this is one that we can pretty straightforwardly compute. So watch me draw an incredible cube here. Watch you. I'm going to do that thing where like you draw two squares, and then you just go boom, boom, boom. And look at that incredible cube. Wow, maybe I should drop out of math school. Haha, only kidding. So the cube is going to have 6 surfaces. It has 6 faces. Okay. Kind of like kind of like some of these haters. They're multi-faced. 2 faces, in this case 6 faces. There are 6 faces, and the area of each face is, well, let's see. So this, since it's a cube, and we are told the length of an edge is x. So each of these, so both the base and height of each face is x. So 6 faces, again, like some of these haters, and the area of each face, well, it's just going to be the area of this x by x squared of each face is x squared, which means that the surface area is going to be 6 times x squared. Okay? So far, so good. Now, we want, what information are we looking for here? The rate of change of the surface area as a function of x. So we want rate of change of surface area as a function of x. Or, in other words, we want d surface area dx. So we're going to follow the same basic procedure we did in the first problem. So we're going to take the derivative of both sides. So differentiate our equation for surface area. So differentiate surface area equals 6x squared with respect to x. The reason that we are doing it with respect to x, and I'll put this in green, and so we can see that connection. We want to differentiate it with respect to x because we're looking for the derivative of the surface area with respect to x. That's what we are told we are looking for. Okay, so let's go ahead and do that. So when I differentiate the left-hand side, well, all that I get is derivative of surface area, or DSA dt. This is not official notation, this DSA. That's just my notation. Right, because again, we're treating this like whenever we differentiate it, we just multiply it by d whatever dt, in this case d surface area dt. Now the left-hand side, we get 12x, and we don't need, hang on a minute. Do we want to do, so then, but x, you'll remember, oh my gosh. this should be d surface area dx. There we go. Now 12x, but x, you'll remember, is a function of t. So this dx dt, we put that in there because x is a function of t. So this is basically chain rule. Okay. So let's go back and look at what we want. So we want the change in the surface area when x equals 2. Okay, so let's go ahead and plug in x equals 2 equals 12 times 2. Let me put that in blue, and then I'm going to do this fancy thing. 12 times 2, where the 2 comes from this. All right. Now we have to multiply that by dx dt. Well, dx dt, we're told that the length decreases at the rate of 2 meters per minute. So it seems to me like dx dt, this means that dx dt equals minus 2. So that's 12 times 2 times minus 2. And that, 12 times 4, but it's a negative, so I believe the answer should be minus 48. It would be what? Meters squared per minute here. Yeah. Okay. So let's go ahead and circle this guy. And let us, MyMathLab says that we are correct. So here we needed to find our formula for surface area. And then once we had that, we had to think about what we were looking for. We were looking for the rate of change of surface area with respect to x. Okay, the reason that we know that is because it says when x equals 2 meters. If we were told when t equals something, then we would be looking at how, hang on a minute. Ugh. The reason that we want the rate of change of surface area with respect to x, because if we look at the formula that we derived, the formula which we derived for surface area only involves x. So surface area changes as x changes. Okay. But then whenever we took the derivative, we needed to take into account the fact that x is a function of t. And so that's why we had to multiply there by dx dt. Okay. The second part of this problem I'm going to leave to you. It basically asks the same question, but with volume rather than surface area. Okay. So now let us do problem 5. Problem 5 says a 10-foot ladder. So this is going to be another related rates problem. Is leaning against a house when its base starts to slide away. Oh no. I hope that nobody's on it. Jeez. When its base starts to slide away. By the time the base is 6 meters from the house, by the time the base is 6 meters from the house, the base is moving away at a rate of 16 feet per second. Okay. There are 3 parts to this problem. I think we'll go ahead and do all of them, but I suppose that we can see how things go. To start, we want to know what is the rate of change of the height of the top of the... Actually, why don't we go ahead and draw a picture first? Why don't we draw a picture first, because that picture I'm thinking might be helpful for all of the parts of this problem. So we're given a picture in this case. The picture, I'm going to sketch it very minimalistically, but it looks like this. So we've got our y-axis. I'll try and make it big so that it's nice and clear. And then we've got the x-axis over here. So this is y, x. Okay, so then we've got our ladder. So it looks like that, say. And this angle in here is called theta. That's what they're calling it. The ladder is 10 feet, so this right here is 10 feet. They're calling the height, this is y of t, so this is y as a function of t, and the base is x as a function of t. So that length is x of t. Okay, so this is our ladder up here, and yeah. Okay. So now let's go ahead and jot down what they're looking for in part A. So in part A, we are looking for what is the rate of change of the height of the top of the ladder. Alrighty, what is the rate of change of the height of the top of the ladder? So here, really what we want to do is, so what are they asking here? And it looks to me, what are they asking for? It looks to me like they are asking for the change in y over the change in t. Why do I say that? Well, the height is given by y of t, and they're looking for the rate of change of the height of the top of this ladder. So we need to find dy dt. Well, first we should probably find a formula for y. Okay, so let's find a formula for y. And let's see here. So if we look at our picture, it looks like, so we've got a right triangle, and we know that the hypotenuse is 10 feet, and we have this angle theta in there, and we have x of t. Well, it looks like they're giving us information about x. So let's go ahead and look at the information which we're given. By the time the base is 6 meters from the house, okay, so this is saying x equals 6. When the base is 6 meters from the house, that's saying that the bottom side is 6. The base is moving away at a rate of 16 feet per second. So in this case, it looks like dx dt equals 16 is what they're saying at x equals 6. So it looks like the first thing that we want to do, well, y, so from the Pythagorean Pythagorean theorem, I totally blanked on, I don't know. We see that x squared plus y squared is going to equal 10 squared, because the base is x, the height, right? We got a right triangle with sides x and y and hypotenuse 10. Even as the ladder slides, its length isn't changing. So we got x squared plus y squared equals 10 squared. So if you plug in x equals 6, because that's what we're interested in, we get 6 squared plus y squared equals 100. So that's 36 plus y squared equals 100. So that is y squared equals 64. And that is y equals 8. All right, that's good. So we know that y, that's not really our final answer, so let's not circle that. But we do have that y equals 8 when x equals 6. And we now can see that we have a formula for the change. We can use this guy, x squared plus y squared equals 10 squared, to start to derive a formula for the rate of change of y. So I'm going to take the derivative of both sides of this thing with respect to t, and I'm going to get 2x dx dt plus 2y dy dt equals 0. Now notice, this is great news, okay? This is kind of a place where we can check ourselves and say, okay, are we on the right track? Well, I have a value for x, right? I'm at x equals 6. And I also have a value for dx dt. And I have a formula. I now have a value for y. So I have something for x. I've got something for x. I have something for dx dt. And I have something for y. And dy dt is the thing that we're looking for. So this is great news, because that means that we have all the information which we need. So let's go ahead and solve this now. So this is the same as saying 2y not equals 2y dy dt equals negative 2x dx dt, which means dy dt equals minus 2x dx dt over 2y. We can cancel off our 2's, dy dt equals x dx dt over y. And now we can plug in. So plug in our values, and we get dy dt equals, okay, well, x was 6. The change in x over change in t was 16. And y was, oh, I dropped a negative at some point. See, if we were in a classroom, then you could call me on that. So we should have a negative out front of everything here. So negative 6 times 16, and then y we said was 8. All right, well, 16 and 8, that reduces to just a 2, so I believe this is negative 12. Okay, and that should make sense, because the fact that it's negative makes sense, and this is another place where we can check ourselves and make sure, in mathematics, sometimes we call this a sanity check. So kind of as a sanity check, should the change in y over change in time be negative? Well, if you look at our picture, we can see that as this ladder slides farther and farther out, the height is going to get smaller, and it's going to get closer and closer to the ground. So y is going to get smaller. So as t increases, as time increases, y should get smaller. So look at our picture and think about it, and indeed, yes, it should. So it doesn't quite check the value of 12, but it does make sense that our answer is negative. All right, great stuff. So that is part A. Part B says, at what rate is the area of the triangle? Is the area of the triangle formed by the ladder, wall, and ground changing then. I think by then they mean at t equals, at the point x equals changing then. So when x equals 6. At what rate is the area of the triangle formed by the latter wall and ground changing? Well, first things first, we're going to need a formula for the area of that triangle. Need a formula for area of the triangle. So of course we all know the general area formula for a triangle, right? In general, the area is 1/2 base height. So area equals 1/2 base height. And in this case, it looks like the base of the triangle is given by x, and the height of the triangle is given by y. So in this case, the area is 1/2 xy. So we want the change in area over change in time. So we differentiate with respect to t. Differentiate with respect to t. And doing so gives us dA dt on the left equals 1/2. And it looks like that's just going to be dx dt, dy dt. Okay, well, we know these two values. Dx dt, that's the one that was given to us as 16. And dy dt, we just found that was -12. So I believe that this is how the area is changing at this particular time. And let's see, that comes out to -96. I suppose I should put units feet squared per second. Okay, so in this problem, we did, did I do something silly? I think I did something silly at some point. The area is 1/2 base times height. Hang on a minute. 1/2 dx dt, dy dt. Oh my goodness. Did I do something silly? 16. Did I copy 8? What did I? Hang on a minute. I think that I made a mistake somewhere. You all are probably looking at this, screaming it at me, like, oh my gosh, how are you not seeing this? So the area is 1/2 base times height, right? And so choose an equation. Choose the equation with respect to t and solve for dA dt. Yeah. Dx dt, we are told that x equals 6. Yeah, dx dt is 16. And the -12 for dy dt is certainly correct. So dA dt equals 1/2 times 8 times -12. dA dt. Oh my gosh. Okay, I paused the video for a minute to look at this and realize what I did wrong. Oh man, this was just lazy. It wasn't lazy. I didn't pick up on the fact that we need to use the product rule here. So no, need to use product rule because I have x times y. Need to use product rule. Oh my goodness. See, it happens to the best of us. We all forget So don't worry about it if it happens from time to time. Need to use the product rule, silly. You silly banana. Okay, let's try this again. Take 2. So dA dt equals 1/2. Okay, so now I have, this formula is still good, xy. So I'm going to first take the derivative with respect to x. I get dx dt times y, plus now I have 1/2. Leave x alone and take the derivative of y. Now we can plug in our stuff. Okay, so equals 1/2. Dx dt is 16. Y we said was 8. That was just a computation we did earlier. Plus 1/2. X is 6 here. And dy dt we calculated as -12. And so here we go. Now we're cooking. This first part comes out to 64. Second part, 6 times 12 is 72. Cut that in half and negate it, -36. I'm pretty sure that we should be at 28 feet squared per second. Let me double check myself this time. Come on, baby. Come on, baby. Yes, sir. 28. In this case, feet squared per second is our unit because we're looking at area. Okay, so we need to be careful here because our formula multiplied x and y, so we needed to use the product rule. But other than that, it was fairly straightforward. Find a formula for area, and then take the derivative of both sides with respect to time, because we wanted to find dA dt. Okay, see, everybody makes mistakes. It is okay. Part C asks at what rate is the angle, so this is where that angle theta we labeled a while ago is going to come into play, is the angle between the ladder and the ground. Ooh, this is a tricky one. Changing then. And again, by then, they just mean at x equals 6. Man, how do we want it? This one is tougher. This is a tough one. So let's go back and look at our picture again. Well, first of all, what are we going to look for in our picture? We need a formula for theta. For theta. So if we go up and look at our picture, we have theta is this angle, and your boy SOHCAHTOA tells me that tangent of theta is going to be y over x. Yeah, we good with that? So tangent of theta equals y over x, and okay, that's great, Bailey, but we want a formula for theta, not tangent of theta. So what do? You hit both sides of this with arctan, apply tan inverse to both sides, and we get tan inverse of tan of theta equals tan inverse of y over x. Now, tan inverse tan of theta, the whole point of tan inverse and tan is that they cancel each other out, and so I'm left with tangent inverse of y over x equals theta. So again, take the derivative of both sides. So now differentiate with respect to t. Differentiate with respect to t. Okay, so on the left-hand side, I just get d theta dt, which is what we are looking for ultimately. And okay, so let's look at the second one, because the second one is not easy. So we need to differentiate arctangent of y over x. Well, recall, so let's slide down here for a minute. So the derivative of, let me use a different variable. Let's just use a new variable, I don't know, a. Of tan inverse of a, you'll recall, is 1 over 1 plus a squared. Now our function here, so tan inverse of y over x, so if I'm going to take that derivative, I'm going to have to, so this means that d dt of tan inverse y over x is going to be 1 over 1 plus the inside, in this case y over x squared. And then I'm going to need to multiply that by the derivative with respect to t of y over x. Okay, well that's not a trivial derivative either. That is one that we're going to have to think about. And for that, we're going to have to use quotient rule. So now we use quotient rule. And we find that the derivative with respect to t of y over x. Okay, so that's going to be the derivative of y with respect to t times x minus y times the derivative of x with respect to t all over x squared. Okay. So it looks like our derivative is going to be, so whenever we plug all of this stuff back into our formula up here for d theta dt, we're going to end up with 1 over 1 plus y squared over x squared times, and then that derivative was this fraction. It was dy dt times x minus y times dx dt over x squared. Okay. Now again, we have all of our values. So I have x equals 6, dx dt equals 16. I have y equals 8 and dy dt equals minus 12. In the interest of time, I'm going to leave it there. However, that is how we would go about this problem. Okay, I was going to do problem 6. Now, as I look at the time, I'm thinking that's probably not going to be the best idea. It turns out to be it's kind of similar, certainly easier, I would say, in my opinion. So yeah, I will leave problem 6 to you, but it's going to follow fairly similarly. Let's instead jump to problem 11 now. And this is where we're going to start doing some of the chapter 4 stuff. So 11, find the extreme values of the function and where they occur. Of the function and where they occur. Okay, so the function is y equals 7 e to the 3x plus 7e times negative 3 to negative e to the negative 3x. Okay, so remember the way that we attack extreme value problems. The way that we attack these is so we want to find all the critical points. And that is where y prime equals 0 or undefined. If we had endpoints of an interval, we would also have to check those for extreme values. But in this case, this function is defined over the whole real number line. So we don't need to check endpoints here because our function isn't defined just over some closed interval. To check endpoints, because there are no endpoints. It keeps going either way. It never ends. Check endpoints because there are none. But normally, we also need to check the endpoints of the interval for extreme values as well. So let's go ahead and take the derivative. Okay, so we get y prime equals, okay, I'm going to do this one a little bit quicker than perhaps I've done these e to the 3x type things before. So let's think about how we chain this. Well, the derivative of e to the x is just e to the x. And then we need to multiply that. So we're going to start with our 7e to the 3x. We're going to leave everything alone because the derivative of e to the x just leaves everything alone. And then we need to multiply by the derivative of the exponent, which in this case is just 3. The other derivative then will work similarly, and we'll get 7e to the, I'll write a plus, 3 plus 7e to the 3 to the minus 3x times negative 3. So this comes out to 21e to the 3x minus 21e to the minus 3x. And so we are going to set 0 equal to that. Okay. And doing so, if I add both sides, 21e to the minus 3x to both sides equals 21e to the 3x. Divide both sides by 21, and I have e to the minus 3x equals e to the 3x. Okay, well, let me think here. Now this means if e to some power equals e to some power, well, then those two powers had better be equal. So that means that negative 3x equals 3x. And this means that negative x had better equal x, but that's only possible if x equals 0. Okay, so x equals 0 is my critical point, is, in fact, in this case, the only critical point. The derivative, so the derivative here, this derivative is defined everywhere. So it's never going to be undefined, right? It wouldn't be defined somewhere if like we were taking the square root of a negative number or if we were dividing by 0, but we're not doing that here at all. So x equals 0 is the only critical point. Now, if we look at our function, so if I plug in, so now to determine what's going on here, we plug in x equals 0, and I get y equals, let me see here. So e to the 0 power is just 1, so that's going to be 7 plus 7, that's going to be 14. Now we want to look at what is happening to the left and to the right of this. So what is happening to the left of x equals 0? Well, there are two ways of doing this. We can plug in a value. Well, we can plug in a value of x less than 0 into y, or the other thing which we can do is the same thing, plug in a value of x less than 0 into y prime, Okay, and we'll interpret those results differently. So let's do both just to see how they work. If I plug a value of x less than 0 into y, let's see, if I plug in x equals -1, then I get 7e to the -3. So then I get y equals 7e to the -3, and then plus 7e to the 3. And then I want to ask myself, is this greater than, in this case, 14? And man, I don't know off the top of my head. Actually, yes, it is. It is, because e is like 2 point something. And so, yeah, this is certainly true. So, yes. Okay, I should have given myself more space. If I plug it into the derivative, x equals -1, well then I get 21, so y prime equals 21e to the -3 plus, or minus 21e to the 3. And we want to ask ourselves, is this thing greater than 0? And in this case, the answer is no. So what these two pieces of information tell us, they tell us the same story. They tell us that my function, so at x equals 0, I'm here. So this is 0, 14. This first piece of information, the way that I would interpret that it's greater, that at x equals -1, I'm greater than 14, that tells me that at x equals -1, I'm like up here somewhere. What the second piece of information tells me, that the derivative is negative, right, because it's not greater than 0, greater than or equal to 0, really. What that tells me is that it's decreasing. Now, either one of these pieces of information is enough. We only need to do one of those things. Only need to do one of those things. Okay? So whichever one you feel comfortable with, depending on the situation, one might be easier. But we also have to know what is happening to the right. It looks, what is happening to the right? The reason that we have to do that, well, at first glance, it looks like this is going to be a minimum. This 0, 14 is going to be a minimum. However, it's possible that the graph continues to go down, in which case it's actually not an extreme value at all. It's neither a maximum nor a minimum. So this time I'm just going to plug in, so plug x equals 1 into the formula for y, and I get 7e to the third plus 7e to the -3rd. So y equals 7e to the third plus 7e to the -3rd. And that is certainly greater than 14, which tells me that my graph then, after it hits 0, 14, is going to go back up again. So what this allows me to conclude is that at x equals 0, we have a relative, actually in this case a global, or an absolute minimum. It's a global minimum because this is the only critical point. So it's impossible. So that means that this is the only place that could possibly be a maximum or a minimum on the graph. So that does it for us. And it looks like in my math lab, they want you to put in an ordered pair. So really, I suppose we should write 0, 14. All right, the next problem, which I will do, is 13. So 13, I love these problems as well. In this one, we are going to find the critical points, domain endpoints, and local extreme values for the function, and local extreme values for the function. The function we are given is y equals x times the square root of 16 minus x squared. And so again, we are going, well, first of all, actually, why don't we start with domain endpoints? So if we look at the domain, in this case, we have the potential problem that we cannot take the square root of a negative number. So I need 16 minus x squared to be greater than or equal to 0, which means that I need 16 to be greater than or equal to x squared, or I need 4, I need plus or minus, I need 4 to be greater than or equal to the absolute value of x. In other words, I need x to live between -4 and +4. So this is our domain. So here we have endpoints, x equals -4 and x equals 4. So whenever we are checking for extreme values, we will need to check these points as well. When checking for extreme values, we'll need to check these. Okay, again, the previous problem we didn't have endpoints, so we didn't have that problem to worry about. Okay, so now let's go ahead and find critical points. So critical points, and remember that's asking where is, are we told, where is y prime equal to 0 or undefined? Undefined. Well, y equals x root 16 minus x squared. So to take the derivative, we're going to have to do product rule. So product rule. Okay, so first I'm going to take the derivative of x, and I just get 1 times the square root of 16 minus x squared. And now I'm going to leave x alone, and I have to take the derivative of root 16 minus x squared. Well, how do I want to do that? Well, I'm going to write root 16 minus x squared as 16 minus x squared to the 1/2. So now, that means that the derivative, I'm going to have to apply the power rule and the chain rule. So by the power rule, I can bring that 1/2 down front, and 16 minus x squared to the -1/2 now. Now by chain rule, I need to multiply that by the derivative of the inside, and that is -2x, which is just power rule. Okay, so this right here, this is the chain. So plugging this in up here, so that's x. I've got 1/2 and a 2, so that cancels. And I get x times -x, 16 minus x squared to the -1/2. And let me go ahead and rewrite y prime down here to make it easier, to make it more digestible. Square root of 16 minus x squared minus x squared over root 16 minus x squared. Okay, so here we ask ourselves, So if I set 0 equal to this, so 0 equals root 16 minus x squared minus x squared over root 16 minus x squared. Well, let me go ahead and add this x squared over that fraction both sides. X squared equals 16 minus x squared. Remember, we're setting 0 equal to this so that we can find where that derivative is equal to 0. Okay, now I'm going to multiply both sides by the square root of 16 minus x squared. On the left, it gets rid of the fraction, and on the right, the radical goes away. So this is the same as 2x squared equals 16, or in other words, x squared equals 8. So x equals plus or minus root 8, or in other words, plus or minus 2 root 2. Okay, so I have these 2 points. So we have these 2 points for x. X equals plus or minus 2 root 2. My domain is -4 to 4. So we should ask ourselves, are these points in our domain? Because if they're not in our domain, then we don't need to check them for extreme values. But in this case, they are. That's because root 2 is smaller than 2, which means that 2 root 2 is smaller than 4, and -2 root 2 is bigger than -4. Now, we should also notice, so in this case, y prime is undefined somewhere. In fact, it's undefined if this denominator, root 16 minus x squared, equals 0, because then I'm dividing by 0 here. Oh, what? Dividing by 0. And that is the same as x equals plus or minus 4. So that means that the critical points in total are plus or minus 2 root 2 and plus or minus 4. Notice that in this case, these the plus or minus 4 are the same as our endpoints. No, endpoints in general are not critical points. They sometimes can be, like here, but not always. You do have to check them for extreme values, but they're not technically critical points. Okay, so now let's check these points for extreme values. Check these points for extreme values. And so the way that I learned how to check, and I suppose we could have done this last time too, but this time we have more points to check. So I was taught to draw out a number line and label all of your critical points. So in this case, we have -4 here. The next one is going to be -2 root 2. It doesn't have to be to scale at all. What matters is just going to be the order. And 4. And so what we want to do is find out what is going on over each interval and at the endpoints. So first let's plug in, so let's indicate, so at -4, let me see, if I plug -4 into y, then I get 0, because it looks like I'm going to have y equals -4, but then inside I'll have 0. And similarly, if x equals +4, then I'll have 0 there as well. So at these 2 points, y equals 0 and y equals 0. Now, what if x, what if x is -2 root 2? Well, so what we should do is we should check Yeah, we need to check these intermediate points. So negative 2 root 2. If I plug that in, let me see. So plug in, so x equals negative 2 root 2. Well, then I'm going to have negative 2 root 2 times this is square root of 16. And then it looks like it's going to be minus 4 minus 8. Yeah, 16 minus 8. Because 2 root 2, that's just 8. And I square that. So it looks like that's minus 2. And then the 2 in here can multiply through. So minus 2 root 16, and that's minus 8. So here, at negative 2 root 2, I have y equals minus 8. And at 2 root 2, let's see, I'm similarly just going, everything's going to be the same except it will be positive. So y equals 8. And so now what we can conclude is that I have, let me see, so the extreme values, well, at negative 4, so negative 4, 0. So I can see that from negative 4, when I move to the right, I'm going to be decreasing because I'm going to go from y equals 0 to negative 8. So that means that negative 4, 0 is a local max because we get smaller to the right. Then negative 2 root 2, negative 8. It looks like it's going to be our global min because that's our smallest point total. Similarly, positive 2 root 2, positive 8 is a global max because that's the biggest our function ever gets. And at 4, 0, in this case, we have a local min because, again, at 2 root 2, we're bigger than 0, and so we're decreasing to go down to 0. Okay, so these are our critical points. We found our domain. Where did we find our domain? Here we found our domain endpoints, and here we found our extreme values. The way that you do that, I think the number line is a great technique. You plug in your values and you see what's going on. Okay. Wonderful. So that is problem 13. These are taking much more time than I expected. So let me look at the other problems I wanted to do. And I think, okay, I'm going to leave problem 7 to you. I think it's quite doable. Or 17. I was going to do 17 and 15. Those two are very similar. Problem 15 is very similar to this one, which we just did. And 17, I think, is not so bad. So I'm going to wrap up with 18 then, which says show that the function is f of x equals x to the 4th plus 8x plus 2 has exactly 1, 0. Exactly 1, 0 in the interval minus 1, 0. The interval minus 1, 0. So the way that we do this is we want to look at f prime of x. We're going to start with that. Okay, so look at f prime of x. In this case, f prime of x is equal to 4x cubed plus 8. Okay, and now what we're going to want to do is we're going to, so now we want to find the critical points. Okay, so what we're going to want to do is to fill out a number line again. We're going to want to fill out our number line similar to how we did before. Our number line. So on our line, we know that we're going to have the endpoints in this case of -1 and 0. Okay, so let's actually go ahead and plug those things in. F of -1, it looks like will be, that's 1 minus 8 is -7, and plus 2 is -1 plus, or negative, that's, oh my gosh, I totally just lost my train of thought. -5, there we go. So y equals -5 here. At 0, let me see, if I plug in x equals 0, then I just get 2. So this already tells me, so since f of -1 equals -5 and f of 0 equals 2, there exists a 0 of f between -1 and 0, because f is continuous. It's a polynomial. F is continuous. Right? So because in particular, what I'm interested in is -5 is smaller than 0 and 2 is greater than 0. So that means that it's crossing the x-axis at some point between those two. So there certainly exists a 0. But what we need to do is show that there are not multiple zeros. So now let's go ahead and find those critical points. So to find critical points, solve f prime of x equals 0, or in this case, that's 0 equals 4x cubed plus 8. Okay, so then if I subtract 8 from both sides, minus 8 equals 4x cubed, divide both sides by 4, negative 2 equals x cubed, which means that x equals negative, or the cubed root of -2. Okay, so this is the only critical point of the function, and it's not in the interval -1 to 0, right? Because cubed root of -2 is smaller than -1. So, therefore, there cannot be any more zeros. There cannot be any zeros of f between, there cannot be any other zero. There can't, So what this is saying, so now if we go and look at our number line, since there are no critical points between -1 and 0, what this is saying, therefore, let me write it this way. F is increasing, is strictly increasing, in fact, meaning it's never staying the same. It's always getting bigger on -1 to 0. So it can only cross the x-axis. It can only cross the x-axis once. Only crosses x-axis once. And the theorem which we use, basically what this is coming from, so this follows from Rolle's theorem. Okay, again, if there was another zero, if there were two zeros in this interval, well, then there would have to be a critical point between them, because I would have to go up and then come back down and then go up again. But the fact that there are no critical points means that this can't happen.